Welcome to Module 4 of Sensation and Perception Online. This presentation will cover why we don't see color in moonlight, the photoreceptors involved in color vision, theories of color vision, and why some people don't see color. We are able to see under a wide range of lighting conditions. Very dim lighting conditions like moonlight are called scotopic light levels. Although we can see under these conditions, we rely completely upon our rods when we do so. Only rods are sensitive enough to function in scotopic light. All rods produce and contain the same type of photopigment. It is called rhodopsin. So all rods respond to light equally. That is, rods all show the same preference for a particular wavelength of light. Have you ever been out under moonlight? I mean, away from street lamps, flashlights, fires. If so, do you remember how the world looked? Did you see color? Let's consider what happens when all functioning photoreceptors have the same sensitivity to wavelength, as rods do. The figure to the right has three boxes. Box A is the input, that is, the light that is being presented to a receptor. Box B shows the receptor sensitivity to different wavelengths. This particular receptor is maximally sensitive to light with a wavelength of about 545 nanometers, a kind of yellowish green. Box C shows the photoreceptor's output, that is, the rate of neural firing that occurs when a stimulus is presented. Right now, no light is being presented, so box A is completely black. Our first question is, since this photoreceptor responds more to 545 nanometers than it does to other wavelengths, is that enough for us to tell us about color? That is, from its rate of firing, could we figure out which wavelength is being presented? Let's find out. First, let's see what happens when we flood this photoreceptor with intense white light. White light is the summation of all of the visible wavelengths, so box A is completely filled. Looking over at box C, we see that the neuron is firing at maximum. Now let's see what happens when an intense bluish-green light is presented. Box A shows the bluish-green light being presented at full intensity. Box C shows the neuron is firing, but not at a particularly high rate. To continue the experiment, we now present an intense orange light. Box C shows that the neuron is firing at the same rate as it was to the blue-green light. Okay, one more test. Let's present a 545 nanometer light, what this neuron maximally fires to, but at a moderate intensity. Box C again shows the exact same response rate. What does that mean? It means that a single type of photoreceptor is not enough for us to tell what wavelength is being presented simply by monitoring the neuron's firing rate. Since all that our brain can do is monitor neural firing rates, it means that a single type of photoreceptor is not enough to produce color vision. This also explains why rods don't see color. This problem that we just walked through is called the problem of univariance. The bottom figure represents how our color vision changes as we go from daylight vision to moonlight or scotopic vision. Colors that are so vibrant under daylight conditions wash out to grays and blacks under moonlight conditions. Rod vision is like grayscale vision. It is true color blindness. Under daylight conditions, light is intense enough for the cones to function. Cones come in three varieties. S cones are more sensitive to short wavelengths, M cones more sensitive to middle wavelengths, and L cones more sensitive to long wavelengths. Looking at the figure at the bottom, which are the S, M, and L cones? Let me give you a minute to think about it. Okay, not a minute, just a few seconds. Here you go. Did you get them right? Even before we knew that we had three different types of cones, trichromatic color theory already predicted such a system. The theory states that the color of any light can be defined by the relationship between three numbers. In the case of our visual system, those three numbers are the outputs of the three cone receptor types. Let's go back over our earlier experiment to test the idea. To the right, we have box A, the input box, which represents the stimuli being presented. Rather than a single box B, we now have three boxes, showing the sensitivities of the S, M, and L cones. Box C is still the output box, but now it will show the output from each type of receptor. What we will focus on is the relative firing rates of the three receptors. First, we'll present an intense bluish-green light, as we did before. Box A shows the bluish-green light being presented at full intensity. Box C shows that the S produces the highest firing rate, the M the next highest, and the L doesn't hardly fire at all. Now let's present the intense orange light. Box C shows that the S doesn't respond, the M responds a little, and the L responds the most. Okay, now the last test. Let's present the 545 nanometer light at a moderate intensity. The S shows minimal activity, the M shows the most activity, and the L shows minimal activity. So, what have we learned? With three cones, we can tell the difference between lights of different wavelengths and intensities. Different wavelengths produce different patterns of responding. More importantly, by looking at the relative firing rates of the three types of cones, we could figure out what wavelength was being presented. That is, we could reverse engineer the wavelength from the output of those three cones. For our visual system, the relationship between the three outputs defines the color that we see. This flag looks a bit strange, but let's see if we can fix it. Stare at the gray dot in the center of the flag. Do your best to keep your eyes fixated on the dot. Don't let them move. There! Are the flag colors correct now? If you blink, it can help to make the after image appear even stronger. An after image is the visual image that is seen after the stimulus has been removed. In this case, it is a negative after image. But why in the world would we see a negative after image? The relationships between cone firing rates doesn't tell us anything about negative colors. A negative color suggests a positive color, or, well, that's weird. At least it suggests an opponency between colors. The opponent color theory states that perception of color is based on the output of three mechanisms. But, in this case, these mechanisms are an opponency between two colors. The blue-yellow mechanism compares inputs from the S cones and contrasts them with inputs from the M and L cones. Yeah, when mixing light rather than paint, red and green make yellow. The green-red mechanism compares inputs from the M cones to inputs from the L cones. The black-white mechanism is really just a measurement of overall brightness or luminosity. There's no such thing as black light. In fact, we already discussed the black-white mechanism when we covered the center surround receptive fields in Module 2. The blue-yellow and green-red mechanisms work in the exact same way. That is, the receptive fields are, for example, blue center, yellow surround. The colors in the bottom figure are a closer representation of the natural opponency colors. Interestingly, these are the colors used for the rings of the Olympic flag. I met up with a colleague of mine at a conference a few years ago. While eating a breakfast of blueberry pancakes, he revealed that he was colorblind. Since I happened to be interested in sensation perception, I told him that I had recently come across a plug-in for Photoshop that filtered pictures so that they appeared to someone with normal vision as they would appear to someone with color blindness. I had already applied the filter to some images, two of which you're seeing here. So I asked if he would be interested in seeing the images. He was. Notice, by the way, the vividness of these images, how the oranges and reds pop out from the green backgrounds. So I got out my laptop and pulled up the images for him to see. We continued chatting for a while and he began to get impatient. Finally, he asked me when I was going to show him the other versions. I smiled and said, "I already have. I had changed them several minutes ago." He couldn't see that they were different. There are several types of color deficiencies. Monochromacy is the only type that is a true color blindness in the sense that there is a complete lack of color vision. This condition is due to having only one type of cone or having no cones at all. A rod monochromat is extremely visually impaired, as this means that they are completely blind under conditions that are any brighter than moonlight. Dichromacy is partial color blindness due to the absence of one of the three types of cones. Though all types of color blindness are rare, protanopia and deuteranopia are the more common. The images on the right are examples of tests for protanopia and deuteranopia. If you have normal color vision, you should be able to see a 2-digit number written in each image. If you cannot see a number in the image, you might want to take some more tests. The most common forms of color deficiency are called anomalous trichromacy. In these cases, all three cone types are present, but one of the cone types is more similar to one of the others. So, for example in deuteranomaly, M cones are sensitive to longer wavelengths than normal, so they respond more like L cones. This is the most common form of color deficient vision, affecting 6% of men and 0.4% of women. To review, we discussed why we can't see color in the moonlight and ran through a simulation to demonstrate the problem of univariance. We then discussed the three types of cones and the trichromatic color theory and ran through the simulation again. This time we saw that each color that was presented produced a different pattern of activity across the three cones. After seeing a negative after image, we discussed the opponent color theory. There are three opponent color mechanisms: blue-yellow, red-green, and black-white, the latter referred to as luminosity. Finally, we saw some pictures to help us get a sense of what the lack of L cones might look like. and discussed the type of color deficiencies that exist. The most common was Deuter anomaly, which is a type of red-green color blindness in which the M cones behave more like L cones.